In this video, we explore the concept of dilution, the lowering of the concentration of a solute in a solution by the addition of a solvent. When working with solutions in chemical laboratories, we are often required to dilute the concentration of a solution, and this typically involves the addition of solvent to lower the concentration of a specific solute in the solution. In aqueous solutions where water is the solvent, that means we need to add water to the solution to dilute the solute. And typically we want to dilute the concentration of a solute to a specific concentration value. The key here is to realize that the amount of solute in the solution does not change when we add the solvent. So in other words, the initial moles of a solute in solution prior to adding the solvent equals the final moles of the solute in solution after we add the solvent. We can represent this idea slightly differently. Moles I, meaning initial moles of the solute before dilution, that is before adding any solvent, equals moles F, the final moles of the solute after dilution, that is after we've added the solvent. Now we also know that from our molarity equation that the moles of solute in any solution is equal to its concentration, which we typically express in terms of molarity, multiplied by its volume, which is often expressed in terms of litres or milliliters. And so we can take this equation here, moles initial before dilution equals moles final after dilution, and substitute in the molarity times volume term for each of these expressions. So the initial molarity times the initial volume will equal the final molarity times the final volume, or MIVI equals MFVF. And this is one form of the dilution equation. Sometimes you may also see it as C1V1 equals C2V2, where the C1 and the V1 refer to the concentration volume of the initial solution before dilution, and the C2 and V2 refer to the final concentration and volume of the diluted solution after the solvent has been added. So let's look at a typical scenario we might come across in terms of performing dilutions of stock solutions. In this scenario, we are asked to prepare 350 milliliters of a 0.12 molar copper 2 sulfate solution from a stock solution of 1.5 molar copper 2 sulfate. Now, a stock solution is a stable solution of known solute concentration that we store in a laboratory for repeated uses. The concentration of solutes in stock solutions are typically much higher than we would normally require, and they are typically diluted to a solute concentration with a known and specific concentration value. So to solve this dilution problem, we'll use our dilution equation to help out. Mi times Vi equals Mf times Vf. And we will make a note of the information we know and don't know about this scenario. For example, we know the initial molarity of the stock solution is 1.5 molar. The initial volume that we want to extract from that stock solution is unknown at this stage, and in these dilution calculations, that is typically what we are generally trying to determine. We're trying to determine what volume of stock solution we want to extract to get our 350 milliliters of 0.12 molar copper sulfate. We know that the final molarity of copper 2 sulfate we need is 0.12 molar, and we know that the final volume we require is 350 milliliters. So we can substitute all those values into the dilution equation, and we can make the initial volume the subject of that equation. And when we plug those numbers into our calculator, we get an initial volume of 28 milliliters. So in other words, what we're doing here is we are starting with a 1.5 molar stock solution of copper 2 sulfate, and we are extracting 28 milliliters out of that stock solution to put it into another container, typically a volumetric flask. And we add, in this case, a further 322 milliliters of water to take it up to the total volume of 350 milliliters. And what we end up with is 350 milliliters of 0.12 molar copper 2 sulfate. So these dilution equations shown here, they're very useful in being able to determine exactly how much stock solution we need to withdraw in order to make up a specific concentration of a solute with a known volume.